We continue with some examples for the section 3.7, so namely the chain rule. So the first, now actually we want to combine the use of the chain rule with other differentiation techniques or properties that we used in the past. So let's try to take the derivative. We'll start with the very simple example. So let's say that y is 10 plus e to the 10 of x. So now we're combining things from this and previous sections. We learned how to take derivatives of trigonometric functions last week, and so we started with sine and cosine, which were derived using the trigonometric limits that we covered at the beginning of the semester. And for the derivative of tan, we used those derivatives. Sorry. And the quotient rule. So now, so we know how to compute the derivative of tan. We also know how to take the derivative of e to the x. And so now it all boils down to combining everything. So now, what about computing the derivative of this expression? Y prime is, again, we apply this. I'm just gonna do this very I'm not gonna skip any steps just for this example, just to make sure that we see where we are applying everything or putting together all the things that we learned. So this is the same as 10 prime plus e to the 10x prime. Why? Because we're just using the fact that f plus g prime is f prime plus g prime. The next step, well, 10 prime, the derivative of a constant, this is one of the first derivatives we learned, is 0. And then plus the derivative of e to the 10 of x. For this, we use the chain rule. Remember, this is actually one of the, it can be differentiated directly using the chain rule, realizing the 10 is the inside function and e to the x is the outside function. But there's also theorem 2, which we saw in the last video, which tells us immediately that this is e to the 10x times the derivative of this exponent. But we learned last week the derivative of 10 is secant squared of x. So in the end, we just get e to the 10x times secant squared of x. In case you don't remember to derive the derivative of 10, you should memorize it. That's for sure. But in case you don't remember for this lecture, since we just covered it last week. Oh, yeah, as I said again, the first advice is to just memorize it. And the second thing is, the derivative follows from the derivative of sine, which is cosine, the derivative of cosine, which is minus sine, and the quotient rule. So what you're going to end up with sine squared minus cosine times cosine, which is cosine squared, and minus minus becomes a plus. So you get sine squared plus cosine squared, all of that divided by cosine squared using the quotient rule. Sine squared plus cosine squared is 1. So you get 1 over cosine squared, which is just secant squared. So that's, so this is actually just a final answer. I don't know why I continued writing. But so this is the first example. So remember now, memorize the derivatives of all the trigonometric functions. Not only it is required, sometimes, I don't know, it depends on what happens. This is a very strange year. And so we may give you the formulas for the derivative. I don't know. I would tend to think that no, because we don't do that. You're supposed to learn them. I don't know what strange thing may happen, what may be decided for the second midterm. But generally, you need to memorize the derivatives of these sine, cosines, and everything, and all the other trigonometric functions, tan, secant, everything. But even if we were to give you these formulas, that it is much quicker, and you can save a lot of time by simply memorizing these things instead of looking them up during the exam. Okay, so that's one thing. So no, it's okay. Well, that's one piece of advice. So now, let's move on to the next example. So 5x cubed plus 9x, if we have to the minus 1/4. This is something that we may be asked to differentiate. So this is a polynomial raised to a power. So this is just an application of the theorem 2, part 2 or part B, I don't remember. But it's the second part. No, this is first part actually. It's just the function to a power. Remember what we said? We can only apply that rule when the power is a number, which is the case here. It's minus 1/4. So y prime will be equal to minus 1/4 when we bring the exponent down. 5x cubed plus 9x. Remember, this is our g of x. This is our g of x. And then, so g of x to the minus 1/4 minus 1. Minus 1. And times the derivative of g. So g prime, which is what's inside. So remember, it's 5x cubed plus 9x. Prime. Don't forget the parentheses. They're really needed. And minus 1/4 minus 1 becomes minus 1 minus 4, so minus 5, and that over 4. And the derivative of 5x cubed plus 9x is 15x squared plus 9. At this point in the semester, we should have no trouble differentiating polynomials. This should be like immediate to all of us. This exponent here, let me just rewrite it because this is just an exponent for the first polynomial. It's not. This is multiplying. This expression here is just multiplying this, not the exponent. And so this is our answer for this second problem. And it's just an application of the first part of the generalized power rule, using the chain rule. So one of the consequences of the chain rule. So another problem, another example. Y, say, equals sine of the square root of x cubed plus 2. Okay, now this is just a straightforward application. So you have the outside function, which is sine, the inside function, which is the square root, and then you have, okay, so you have three functions, so the square root, and then yet another inside function, which is x cubed plus 2. And in this case, we just proceed like before. So we, in steps, when we compute the derivative of this, what's inside, we need to apply the chain rule again. So you always take derivatives and evaluate what's inside, take the derivative of what's inside and evaluate what's inside, and so forth, and multiply all these things. So here, This is just the derivative of what's outside, which is sine. The derivative of sine, which is cosine. Evaluated what's inside. What's inside is the square root of x cubed plus 2 times the derivative of what's inside. So the square root, the derivative of the square root is 1 over 2 times the square root. Evaluated what's inside, which is x cubed plus 2 times, and now the derivative of what's inside, the last thing, this is the polynomial, and we know how to differentiate that. That becomes 3x squared plus 0, right? Because the derivative of 2 is 0. Okay. And yeah, I mean this is what it is. Let's see one last example. Slightly more complicated. Probably you're not gonna see anything like this. You're not gonna be asked to do anything like this, especially this year. But nevertheless, it's good practice, and if you're able to do this, then you should have no problems for the exam. So e to the square root of, say, cosine x squared plus tan of x cubed. So this is a very complicated looking, it's kind of a complicated function. It's not very nice looking one, but it just boils down to keeping track of everything that's inside of what's inside and everything. So it's still like an application of the chain rule, just that it takes more steps. But it's nothing really more complicated. You shouldn't feel intimidated by expressions like this. So if you're organized, you'll compute this following all the steps, and you'll do fine. Y prime then will be, what is the outermost function here is e to something. The derivative of that is just e to the something, and you evaluated what's inside. What's inside is this whole exponent here. So this is the e to the square root of everything that's inside the square root. So x squared plus 10 x cubed, and then times, and then you keep going inwards. So now this is the new function, the square root of cosine of all this whole thing inside. So you take the derivative of then the next thing. So that's the square root. The square root is a second function. Everything else is inside the square root. So you take the derivative of that, and that becomes 1 over 2 times the square root again of everything that is inside the square root. Cosine of x squared plus tan of x cubed. And now we multiply this by the derivative of what's inside the square root, which is cosine of this whole thing. And to compute that again, what is the outermost function now? What's inside the square root? Of what's inside the square root, the outermost function is cosine. Remember, we're forgetting about e to the square root. I mean, you're just moving in layers here. We're moving inwards. So this is the derivative of cosine. The derivative of cosine is minus sine. And again, we evaluated what's inside. So x squared plus 10 x cubed. Okay, so we keep moving inside, and we now have to compute the derivative of this expression inside. So yeah, then again we have 2x plus 10 of x cubed prime. But And this is just to stress the fact that we need to take derivative one more time, derivative one expression one more time, and apply apply the chain rule one more time to a part of an expression that is inside the last function we encounter when we go when we move inward. So now to take the derivative of this, we again look at this function. This is tan of something, so the outermost function is tan. The derivative of that is secant squared. Secant squared of what? What's inside? So that's x cubed. And now, finally, we take the derivative of the last function, which is x cubed, which is sitting inside, what was sitting inside of tan, and that's 3x squared. Simplifying the power rule. And this whole thing is the derivative of y. And yeah, so that's basically it. I mean, you shouldn't expect to find anything this complicated, but I'm just saying. I mean, then if you're able to compute this derivative without any trouble, then you're done. You're good to go. You won't be asked to do anything this complicated. So the next thing we're going to be doing this week now, so we're done with this. So the next thing is we're going to be going over implicit differentiation, which is a technique that allows us to compute derivatives at least at certain points of functions that are not given to you as in the form f of x is some expression depending on x. So it's something that may be, as the name says, defined implicitly. So this is a relation satisfied by x and y at the same time, and that defines a function implicitly. So they're given any x, there's only finitely many possible values of y for which this relationship will be met. A canonical example is the case of the circle, although that's a kind of a bad example because you can solve for y in that case. But the most important application is when the variables x and y are so intertwined in some constraint or some expression involving these two things that it's impossible to solve y in terms of x. And in those cases, the only alternative you have, if you want to find out the derivative, is to differentiate implicitly. And in that case, you will end up seeing that you will obtain an expression for y prime which will only depend on x and y. And yeah, and of course it has to depend on y because whenever we ask you to differentiate things implicitly, we have to give you the point in R2, so x, y. So the derivative of a certain y at the point, say 1, 0, for example. Something like this. So you know x, y, and so y prime will be given to you as a function of y and x, so that's not a problem. But we'll get to that in the next video, and if you can go ahead and try to read in advance what this is going to be about, it would be great. So that will save us some time, and probably going to get more out of the lecture.